So in this lecture, we will be doing a handwritten derivation of the previous lectures. This is what I call a dog food lecture because I'm actually dog fooding my own content, as they say in software engineering. This is also to give you a chance to write along without having to pause the video every few seconds. Okay, so we'll start with what our model is. The model is a line. So we have y equals wx plus epsilon. So this is the output, this is the input, this is the slope of the line, and this is noise. So the noise is characterized by a normal distribution with mean 0 and variance sigma squared. Okay, and there's no bias term on this line, since we can absorb that into the x vector. All right, so on the next slide here, we have a way to represent multiple data points. So as you know, our training data will consist of pairs of xy data points. And so we'll say we have n pairs, so we index them using the letter I. And we have I going from 1, 2, 3, all the way up to big N. Okay, and so we say y sub I equals w times x sub I plus epsilon sub I. And this gives us an opportunity to say that epsilon sub I is sampled from the standard normal IID. So that means independent and identically distributed. And it has the same distribution as above. So independent means statistically independent, and identically distributed means they all come from this same distribution. Okay, so after we collect these data points, so we can imagine our data points are, some x1, y1, x2, y2, and so forth. So you collect these on a spreadsheet or something like that. And now you would like to find w. So how do you find w? Well, we need some loss function to minimize. And w would be, the best w would be the w that minimizes this loss. So for linear regression, our loss function is the sum of squared errors. We say SSE is equal to the sum from I going from 1 up to n, y sub I minus y hat sub I squared, because we want everything to be positive. Okay, so in order to actually find w, we need to use calculus. So our loss function basically is a parabola like this, and we want to find this bottom point here. And it just so happens, if you remember from your calculus, that this point is where the derivative is 0. So if we call this thing j, this is where dj by dw is equal to 0. And this is the only point where this happens, because this is a simple quadratic function. Okay, so in order to solve this, we're going to write down our loss function once again. And we're going to replace y hat sub I with w times x sub I. So we know that y hat sub I is equal to w times x sub I. And so the next step is to find the derivative. So we'll write dw dj by dw. And this is a pretty simple derivative. It's really just the sum of, or you can think of it as y1 minus wx1 squared plus y2 minus wx2 squared. So you're really just taking the derivative of each of these one at a time and then summing them back up together. But to make it simpler, we can do that inside the sum. So the 2 comes down. This is what we do for a polynomial. The inside stays the same. And then we take the derivative of the inside. So the derivative of the inside, this would be 0, and this would be minus x sub I. Okay, and now, as you know, we need to set this to 0 and solve for w. So we'll just write it down again. Say sum going from I1 up to n to I minus wxi times minus xi equals 0. And we want to find w. So the first thing we can do is get rid of any constants. So if we divide everything by 2, the 2 goes away, and 0 divided by 2 is still 0. And then we divide by -1. So this goes away, and 0 divided by -1 is still 0. So we can rewrite this a bit more simply as the sum from I going from 1 up to n, yi minus wxi xi equals 0. So at this point, we can multiply out the xi. So we're going to multiply xi to this and xi to this. So this gives us the sum for I going from 1 up to n, xi yi minus wxi squared equals 0. And in order to solve this, we can split up the sum. Okay, so that gives us the sum, we'll just say I, xi, yi, minus, now you can bring the w outside of the sum because w is not dependent on I. So w comes here, we have the sum over I, xi squared equals 0. And so perhaps the summations are a bit confusing. This is really just a number, let's call it a minus w times another number, which is b. So remember, we have all the xi's and yi's. These are just numbers. So this is 0, and so from this, you'd know how to solve for w. So we do the same thing. So w is equal to the sum over I, xi, yi, over the sum over I, xi squared. And we usually put a little hat on this to denote that it's an estimate. Okay, so that's the answer. So the next thing we'd like to do is we'd like to solve for the distribution of w hat. So in order to do this, we're going to write down, well, let's write down the title first. Distribution of w hat. And we'll write down what w hat is again. So w hat is equal to the sum for I going from 1 up to n, xi, yi divided by the sum for I going from 1 up to n, xi squared. So we want to know the distribution of this. Now, to make this a little easier, we're going to first do a simpler exercise, which is finding what the expected value of w hat is. So that's not the full distribution, but it's one of its statistical properties. So we want to know the expected value of w hat. What is that? Okay, so in order to find the expected value of w hat, we're going to begin by just taking the expected value of both sides. We'll say E of w hat is equal to E of this whole thing. Okay. But now we have to remember that the x's are not random. The x's are fixed. They're just part of our data set. What is random is y sub I, since, as you recall, y sub I is equal to w times x sub I plus epsilon sub I. So this whole thing is fixed. And this thing is random, since, as you recall, it's normal with mean 0 and variance sigma squared. So if it comes from a distribution like this, it's random. So because of that, y sub I is a function of this, y sub I is also random. So we can say this is actually equal to the sum of I. So basically the expected value comes inside. So we have E of y sub I. And then this is like a constant, a dividing constant. So what we would really like to do is find e of y sub I. And once we find that, we can plug it back in. So what is e of y sub I? Well, we can plug in our model, which we've assumed to be true. So it's w x sub I plus epsilon sub I. And we said this is fixed, right? So this can come outside the expected value because it's just a constant. And then we have e of epsilon sub I. But this is just 0 because the expected value is 0. Okay, so the expected value of y sub I is w times x sub I. So we can plug that in. We can say e of w hat is equal to the sum over I x sub I w x sub I over the sum over I x sub I squared. Now what we can do from the top is we can take w outside of the sum, again, because it doesn't depend on I. So on the top we have the sum over I x sub I squared, and on the bottom we still have the sum over I of x sub I squared. These are the same, so they cancel out. So it's just w. And this makes perfect sense. So the expected value of w hat is w. And because of this, we can say our estimate of w hat is unbiased. Okay, so that was just the starter exercise. Now we're back to our original question of what is the distribution of w hat? So we'll write this down again. Distribution of w hat. What is this? So this time what we're going to do, well, we'll start by writing down our w hat again. Going from 1 to n, x sub I, y sub I, over sum I 1 to n, x sub I squared. Okay, so this time we are not going to do any expected values just yet. We're going to plug in our expression for y sub I. Okay, so what we can do is we can plug in our model assumption for y sub I, which we have assumed to be true. So we'll say equals sum over I x sub I w x sub I plus epsilon sub I over the sum over I x sub I squared. Okay. And now what we would like to do is just simplify this. So basically this is, you can think of it like this. This is a constant, and then we're just expanding the top part. So we have w times the sum over I x sub I squared plus the sum over I x sub I epsilon sub I. Okay, now this would cancel out with this, except when it's over here. So we have w plus, so this thing stays, sum over I x sub I squared, sum over I xi epsilon sub I. And just keep in mind these are separate i's, right? This summation on the top is separate from this summation on the bottom. All right, so the next thing we're going to do is we're going to just say this is equal to a constant called c. So c is equal to 1 over the sum over I x sub I squared. And doing so, we can see that our w hat can actually be written very simply. It's just w plus c, and we can expand the sum too. So we'll say x1 epsilon 1 plus c x2 epsilon 2 plus dot 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 plus c xn epsilon n. So there are a few things we can see from this. The first thing we can see is the expected value of w hat is just w. So if we took the expected value of both sides, we know that the expected value of epsilon is 0. So all of these would go to 0, and you'd just be left with w. The second thing we can see is that w hat is the sum of normals. And we know from probability that the sum of normals is also normal. So we know that w hat comes from a normal distribution with mean w and some variance that we don't know yet. but it's a variance we can calculate because we know the expression for w hat. And so what you want to remember is that a normal distribution is fully characterized by its mean and its variance. So once we find the mean and the variance, we know the distribution. And so when we say we want the distribution of w, what we're really saying is what is the mean and what is the variance. And since we know the mean, now all we have to do is find the variance. Okay, so what is the variance of w hat? So in order to compute the variance of w hat, we'd like to keep in mind some identities from probability that would be useful. So the first one is, what happens to the variance of a random variable when we multiply it by a constant? So if we know that the variance of some variable x is equal to sigma squared, then what is the variance of ax? Now it turns out that this is a squared, sigma squared. So you square the constant. The second thing we want to know is if we have a variance operator on a constant plus some random variable x. This is just equal to the variance of x. And to see why this is, suppose we have some distribution. So this is our distribution of x. And now suppose that we added some constant to all the values. So we moved it over a bit. So this is c. Let's say that's 0. By doing so, we haven't changed the variance. So let's call that sigma. The variance stays the same. Okay, so adding a constant to a random variable doesn't change the variance. And okay, so one more identity we'd like to know. So if we have the variance of independent random variables, so say x1 plus x2 plus x3 and so forth. In general, this is not equal to the variance of x1 plus the variance of x2 and so forth. So we need to account for the covariances as well, unless they are independent. So unless x2 and so forth are independent. If they are independent, then this is true. Okay, so using this, we can now find the variance of w hat. So the variance of w hat is equal to the variance of just our expression from before. So it's w plus c x1 epsilon 1 plus c x2 epsilon 2 and so forth. Okay, so the first thing we see is we don't have to consider the w because the w is a constant. The second thing we can see is that this is just equal to the variance of the sum, which is the sum of variances, because the epsilons are independent, as we established earlier. It's actually one of our modeling assumptions. So variance of cx2 epsilon 2 and so forth. And then we can use the first identity. So the constant gets squared. So we have c squared, x1 squared. And then the variance of epsilon is sigma squared plus c squared, x2 squared, sigma squared, and so forth. And from this, we can see that these are common in all of the terms. So we can factor that out. So this is just c squared, sigma squared, x1 squared plus x2 squared plus dot dot dot. Okay, and that is equal to c squared, sigma squared, the sum over I, xi squared. Okay, so you could leave your answer like that, or you could simplify further, which would be desirable in this case. We just have to remember that c is equal to the sum over I xi squared. And what we had before was the variance of w hat being c squared, sigma squared, sum over xi squared. So obviously this cancels out with one of the c's. So we could say get rid of this and get rid of one of the c's. And now we have sigma squared over sum over I xi squared. Okay, and so what do we end up with? We end up with w hat is a normal with mean w and variance sigma squared over the sum for I going from 1 up to n xi squared.